In this hypothetical scenario, we've got a liquid fertilizer which acts as a poison to one plant and a nutrient to the other. And the number of leaves present after so many days is given by two formulas over here. And if we examine the two formulas, they are exponential formulas. If we were to draw them into decimals or into the calculator, we would be able to discuss and identify them. The exponential function, which is increasing, is 30 e to the 0.003 t for days. And you can see that as t goes to infinity, then our function t goes to also infinity, which is saying that the number of leaves are increasing. This will represent plant B. The other exponential function is shown by the red line, and that will be nt is equal to 120 e to the negative 0.002 t. It shows you that when t goes to infinity, then the number of leaves goes to 0, which means that the number of leaves are decreasing. And that is represented by our plant A. From this graph, it is also evident that there are 30 leaves on the plant B and that there are 120 leaves on plant A initially. Even though we can determine from this graph the time at which the number of leaves on both plants are exactly the same, we might be asked to find the exact time. To do that, we need to work it out algebraically. We will equate the equations of both plant A and B. And we want to solve it for t, so we'll move our numbers around. 120 over 30 is 4, and the negative exponent in here can be moved to the numerator. And as they are both to the same base e, we can add the exponents together. And as I want the t, which is in the exponent, I'm going to ln both sides to help me get that t, because ln e now will cancel, and t is going to be ln 4 over 0.005. Now that is pretty exact, but we can change the 0.005 because 1 over 0.005 is the same thing as 200. I rewrite this as 200 ln 4. If you wanted to know, this is the exact number, but if you wanted to know more or less what that number is, you might have been tempted to write this as ln 4 to the 200 and work out. Now, you will not be able to get an answer on the calculator because 4 to the 200 is too large for the calculator to handle. But if you plug in 200 ln 4 into the calculator, it will give you approximately 277. What you need is the exact answer, and the exact answer would be 200 ln 4. Now, if you want to find the time when the rate at which the leaves are dying in plant A is equal to the rate at which plant B is growing, we will need to differentiate both of these exponential equations to find the rate of each plant. And plant A, when differentiated, will become minus 0.24 e to the minus 0.002t. And plant B will become 0.09 e to the 0.003t. Now please note, if the rate at which the leaves are dying in plant A is equal to the rate at which the plant B is growing, then therefore plant B must be the negative of plant A. Therefore, we can equate 0.09 e to the 0.003, which will be equal to negative 0.240 e to the minus 0.002t. Why am I making this a negative? Well, let's examine two exponential functions. One of these exponential functions will be, let's say, e to the x, and the other exponential function will be going the other way, which means that it'll be e to the negative x. And this is the scenario that we have. If I was to look at a particular gradient, I'm looking at a gradient at this point, and let's imagine that that particular gradient, dy dx, is equal to 2. The gradient which is equal in rate to the other exponential function would be here, and it will be not positive, but it will be negative. But it is equal. It's still, the rate is 2. Rate is 2. But one is increasing and the other one is decreasing. Now, if I just put these two exponential functions into my graphics calculator, I will get, so if you were to graph this into your calculator, and you'll find the point of intersection, it'll be 196 days, which means that the rate at that time is the same, equal, but opposite.